have this. Since Ryan could not be here and Abby is not here. So this is a different topic and very exciting. The figures that I don't cite the references are all from this book. So just to make that clear. And this book, I already put it for you on Canvas if you need to look up some of the details. How many of you are not at all familiar with acoustic emission testing, except for Chaz? Okay, great. I like to play this on the PowerPoint because of the animation. So acoustic emission is different from the other tests that we have talked about. And the reason for that, let's see. Oh, wow. What is going on with this? Recovery? Oh, there is a nice animation I wanted to show you. Okay, looks good. I think, yes. So the main difference between acoustic emission and the other things that you've seen so far is this. Let's say if you have a sample which is under stress, and what we have seen so far is that you have transducers, you place them in different orders, in different numbers, and then you look at that particular time, what is the velocity attenuation, or what is the layering inside your specimen, right? Where is Gigi?
He picks up his homework.
Oh, okay. So now, acoustic emission is different in a sense that the sensor is actually there as an instrumented ear. It is listening. So when something happens, if nothing happens, it doesn't record anything. But then if you are, let's say, pressing a sample, you are creating some micro cracks. So what happens is when you have a crack like that, then you record something. And then if you continue to listen, you are going to record other events. So that makes acoustic emission different because it's a monitoring technique. If you go after the event, after these cracks are already there, and you place an acoustic emission sensor, there is nothing to hear. So it's an active measure. It's a passive measurement. You are basically listening to what's going on. This is the animation I wanted definitely to show you, especially some of you who are not really familiar with this. What happened? I think that would be important. This is not a problem, but sorry about this. Where is this? Where is display? Here. Okay. These things happen. So Gigi, what's going on today? Whenever I try to do something is wrong. So we were just starting to say that what is the difference between acoustic emission testing and everything else. Oh, I said keep changes. This is what I didn't say probably before. And the difference is that acoustic emission testing is listening to the events that are actively happening, basically. And I showed an animation that you missed, and I don't repeat it because it was complicated. I have shown you some of this before. So why it is useful? It is useful as a structural health monitoring tool. For example, now everything probably makes a lot more sense to you. If you want to monitor, here there are two piers of a bridge. There are like two bases. And if everything is okay, if you listen to the pier as a train is going by, you don't see too many events. But if you have cracks, and if the material is close to failure, as the train is passing by, you hear a lot more events. So it is being used for a structural health monitoring. What is the relationship? Let's just go through the objectives then. So what I want to make sure that we are going home with is to understand what is passive monitoring and active monitoring. I give you some principles, what acoustic emission is doing, a little bit of the history because it's interesting, and then we'll talk about what type of sensors, what is the setup that would give you good acoustic emission testing. And then I'll talk to you about how to localize the source and how to characterize it. And in between, you see some applications. Now, we call acoustic emission a passive monitoring test. Why? Because you don't have an active source. Let's compare it to what we had before. You had a source, you had one transducer to send a pulse and you would receive it. This is active. Acoustic emission, there is no source. You just listen to see what is going on, right? So you hear these terms, passive and active, that's what it means. When you have passive, it means that there is no source, basically. And acoustic emission is definitely a passive technique. Now, how does it look like? If you have, let's say, a machine, if you have a machine which is operating, like a washing machine or machinery in a fabric, if you place an acoustic emission sensor, you are going to hear constantly something going on. It would look something like this. If you have cracks popping up inside the specimen because of loading, because of other damaged processes, it would look more like this. You have these burst pulses, then there are quiet times, and then comes another, and comes another. So it's very different. You are just placing a sensor and you just record to see what's going on. So it's a different kind of testing than what you have seen before. What exactly happens? The principle is this. You have a crack which releases the strain energy, and this travels through the material. Wherever you have a sensor, it takes some time for this energy to travel from the nucleation source to that transducer, and then you receive it here. A detection system, like a very simple setup, would look like that. You don't have a source, and that makes the setup in that sense cheaper, because what is expensive is always something which can actually provide the activation. But you will see later that there are some very important issues with acoustic emission testing also that makes things complicated. So we have a sensor, and basically the rest is amplification and filtering. Why we need a lot of amplification? Because when you have an active source, you can control what is the voltage, you can put in as much as you want, so you can control signal to noise ratio, etc. In passive monitoring, something has burst, the energy travels through the material, so the signals may be very tiny. To be sensitive enough, you need to amplify them. So that's why you have preamplifiers, a strong preamplification. And then as I'll show you, you'll have a lot of noise because you're listening and there are so many small things that you can see. So you need to do a lot of filtering. And that's kind of what the basic setup would look like. And some of you are in geosciences, and of course there is a strong relationship between acoustic emission monitoring in industrial applications and seismology. What is the relationship? I mean, the picture is in front of you, but yes.
The source here is the earthquake, and they're passively monitoring, like you say, far away in Germany.
Exactly. So this is the earthquake in San Francisco. It's a picture, and the signals that you see are what has been recorded many miles further in Germany. So there is the analogy at larger scales. This is like basically similar to earthquakes, and that's why that there is a very strong connection between seismologists and people who do non-destructive evaluation using acoustic emission, because the methods are very similar. And more recently, in the context of hydraulic fracturing, we are actually creating artificial earthquakes. So there are man-made earthquakes, and for that also, when you record them, sometimes you would hear the term passive seismic monitoring. In terms of principle and what's going on, is very similar to acoustic emission. You have a transducer and you listen what's going on as you are basically going through the process of fracture. Any questions? Everyone is very quiet. Okay. Okay, so this is about, some applications and why this is important and how different it is. Is the difference between acoustic emission and the other measurements that we see, for those of you who have never seen it before here? Yes? Anu? Okay. So it is interesting to look at the very first acoustic emission setup. This is how it looked like. And this is the first paper in Japanese in 1933, where they actually used a test like acoustic emission. You can do it? Yeah, I know, but is it actually acoustic emission? Okay. Yeah, so it was a earthquake research institute meeting apparently in Tokyo, but I have trusted the translation that I've seen in the source, so I don't know. And in 1933, so they were looking at the bending of a piece of wood, and so they did something very similar to what we call acoustic emission today. So in the old times, and as you will see, still this is being used for very good reasons. When we were doing acoustic emission, we were not collecting the whole waveform. So this is like an example of a burst. In the old times, of course, the sampling rate was low, so that's why it looks very strange. But the acquisition was not very fast. So imagine you have to listen for a long, long time. And the memory is very small, etc. Most of you don't remember, all of you don't remember anything, probably like below terabytes. But everything was much less accessible. So in those situations, this is how it would work. You had to have a pre-selected threshold. You would say, okay, I have this threshold. Whatever goes over, record. And not every point. You would record just the first, second, third, and then the highest, and so on. And then from that, you would extract parameters, of course, you would see that within a certain duration, so then it would get quiet, right? So then that would give you the duration of the event. And then you would have a maximum amplitude. You would know how many points have crossed over the threshold to the amplitude before the amplitude. That's called rise time. That's a nomenclature in acoustic emission. And then you would see how many counts are after the amplitude, and you would only save these parameters. So you would lose the waveform. All you would save are these kinds of parameters. This was how it was being done before, and as I said, still in some of the situations, that's how it is being used, and I will tell you why in a few minutes. If you have any questions, please ask. Now, of course, from 1933 to 2014 has been a long way. So if you look at the state of the art, now there are tiny transducers. You can even have paint-on transducers for acoustic emission. You just paint the transducer, and then you can wirelessly transmit the data, and you can have a lot of transducers. There are challenges with having a lot of transducers, but we will get back to that. So we have come a long way. Another important change that has been made is that as the data acquisition has been faster and the storage has been cheaper, we have had the opportunity to save the entire waveform. We don't just put a threshold beforehand and look for the counts. Also, this is still challenging to do. One benefit of having the whole waveform is that you can also look at the frequency content. Because before, when you only have those counts, most of the frequency information would be lost. But now, this is not the case. Even at that time, people would divide the number of counts per duration, etc., to get a sense of frequency content, but they would not be able to get the power spectrum and see where the peak frequency is and the center. These are two of the most common parameters that people use when they want to classify acoustic emission events. So this is kind of where we are now in terms of data collection. You can collect the data, and you see that from time to time you have a large burst, etc. This is actually 4966 data. So, yeah, it's good to take a minute and think about this parameter base, the old way and the new way. So let's see, here I have the noise signal. So you have the option to have this whole noise signal here, or you can just take those parameters and do a parameter-based analysis. So try to think about in these terms: recording time, storage speed, possibilities to do real-time visualization, and dead time means that how much time you would lose because your system is trying to save the data that you are collecting. So during that time, you won't be able to collect any new events. So that's normally called in our terminology dead time. You can hear that in acoustic emission. Try to see which method you think would be a better method, or what are the advantages of each one. And then there are other issues. One we talked about, frequency domain, the difference between signal and noise. How do we find out? And what are the possibilities in terms of post-processing and information extraction? Talk to each other a little bit about that, especially if this is all very new to you. Try to think and try to have the concept settled down. each other. That is how fast you can save the data on the computer. Yeah, so the recording rate is more like a sampling frequency. How fast you are recording. Storage is how fast you are saving. And that's what you last night when I was walking home, I saw the campus is very alive. Everyone is working. It was nice to see. Exactly. As it's a story, then there is a time when you cannot record and store, so you do some effect. I want to make sure that people who have never seen the video so when you are filming, sometimes it takes time, but at the same time so then basically something can happen. You can have a crash even if it's a very fast graphic processor yeah, it's easier you always have this, none of the data systems that I know they cannot be so fast because it's not just saving the data directly, they can do compressing, making it smaller, and the size of the files are huge. So that takes time, and during that time, the system just cannot record This is so the acoustic emission. This is one of the issues. Basically, the only big issue that we have. Anyway, so let's discuss this. Recording time rate. That is more like sampling rate. How fast you can record. So what do you think? Parameter based, does it have advantage over a full waveform? Yes, probably you can record faster. So parameter based is probably, I just put P, probably has more advantage here. Storage speed. But of course, if you don't have to save the whole waveform, you can also save it much faster. So it's kind of parameter based, and that's why in commercial applications, people a lot of times are still doing that. They are not collecting the whole waveforms. If this is something which is very straightforward, they don't do that. It's just much better. And then if you have only these parameters, you can have real-time localization. So if you have a commercial system, as something is happening, you can actually see exactly where your events are. I have done that before, so I know exactly how it looks like. I have to say that it won't be super accurate. So there may be some weird things you see, but the bulk of what you see is what you expect. Okay. So you cannot really do that with signal-based. And then we discussed at that time with some of you that you are not familiar with this. When the system is recording, then it takes the data, it has to change it to a special format So it can save a huge amount of data in a small piece, and it takes time and it cannot record at the same time. All the systems I know, they have some dead time. They cannot record continuously perfectly. If you just have parameters, step time is smaller. So now it looks like, wow, parameter base is great. No, this is not the case. Because if you have only a few points per waveform, imagine, you can have a lot of noise in this area. You can get things which are not an event at all. So it will be very difficult to decide on whether you have a signal or noise. This is an issue in general in acoustic emission, deciding between what is noise and what is signal. It depends a lot on the application. I give you an example. For example, if you have a loading machine operating, and at the same time you are measuring acoustic emission, you may get a lot of events just because of the operation of loading machine. Like the moment that the loading plate sits on the specimen, something will show up. Anything you do, you will see. So one thing that we found very useful was actually frequency domain classification. The frequency of the, in a certain bandwidth of the events are very different from what you would get from everywhere, and you could separate them. So it's not always the same, and it's not always very straightforward. But when you have all the waveforms, something that you can do, you can go back, look at the whole data set, and then try different things and see what makes sense. This is what we did. That's how we found out that with frequency we can very nicely separate noise from signal. So the point is, if you have the whole waveforms, it would be much easier for you to actually find the correct events, not to mix them up with noise. So here, signal is superior. I already told you about frequency domain analysis. And of course, if we have the signals, then you can go and do a lot of post-processing. You can do classification, do all sorts of things. So of course, it's much nicer to have the whole waveform. So I hope that made the whole idea of acoustic emission clear. Now I want to give you some practical advice. Let's say in your future job, you go to a structural engineering firm and they want to do acoustic emission. And they ask you, so Mervyn, what kind of sensors do you have to buy? It's very important. For acoustic emission, you want to have a very broadband sensor. The reason is you don't know the frequency content of the events that you may have because of a certain damage. So the best sensor would be a sensor which has this kind of a flat spectral values over a long range. I mean, this goes all the way to 1 megahertz. That would be perfect. So you have a broad range. Another important thing, which is equally important, is that you want to have a sensor, if possible, which has a large divergence angle. You want your sensor to see everything happening around it. You don't want something that is just looking in front of it. You don't want that. And just to make sure that you remember some of these concepts, you know, some of the sensors that we looked at that are more like a resonance sensor, these are not very suitable for acoustic emission because, as you can see, the range of sensitivity is small. What is better is this multi-resonance sensor. That would mean also that if you use a resonance sensor within this range of frequencies, of course you are going to be more sensitive. So you see a smaller events better. If you use a broadband sensors like that, you may not be as sensitive because the energy is distributed, but you have a chance to see all sorts of events at different frequencies. So it all depends on the application. If you know the frequency of the events that you expect, you know the range, you may actually want to have a sensor like that so your events look large when you record them, because that's always a challenge. And in case you have forgotten, the divergence was this. I think I gave you some German reference on this. That you see that sensors have different divergence. And here you can see how we actually find this kind of divergence. So for example, you can have a half cylinder and you can have a sensor on the back, and then you measure the amplitude around it. In the institute I was working in before, we were actually using a half sphere. It's a little bit more complicated, but it gives you immediately in two directions the sensitivity, the directivity. What you want for acoustic emission is more like a broader, a larger divergence, or a smaller directivity in a way. Yeah, any questions on the sensors? Concerns? Another thing which is very important for acoustic emission is the coupling. Some of you are familiar with everything, some of you is maybe the first time. For metallic structures, what I've seen is we normally use magnets. That's kind of the preferred way. The problem is that if the coupling is not good, you're going to lose a lot of energy, and acoustic emission events are small enough. So you try to have good coupling to make sure that you get good results. So you want, if possible, you want to have the sensors directly on the sample, not to dilute them or not to make them smaller by going through some other medium, etc. How many? That's another good question. These are a little bit wordy, these slides, because I wasn't sure how much time we have. But the main thing is, of course, the more the better. But, and this but is important. First of all, you want to make sure that if you want to cover a certain area, that the coverage of your sensors overlap and cover the whole area. So this is kind of how you define where to put your sensors. So if you want to do any kind of localization or characterization, you want to have a lot of sensors. You need to have a minimum number of sensors. If your medium is very attenuated, you need to have more sensors. Because if it's very attenuated and you have only one sensor, most of the events don't even get to it. But if you have a lot of sensors, remember the data acquisition, everything becomes slower, the dead time becomes larger, it will be very difficult to handle the data. So you need to find a trade-off between the number of sensors and what you actually want to achieve. Exactly, and it depends on where you want to monitor. If there are places, if you have to decide definitely, you want to have your acoustic emission sensors around the areas of highest concern. Another thing is, if you want to do any kind of localization, any kind of analysis on the data, the best is to have identical sensors, meaning that they have the same spectral characteristics, they have the same kind of sensitivity. Otherwise, it would be very, very hard to analyze that data. What else? So basically, this is everything I said, it's written there. Now, can you get something with one sensor? Yeah. Just to show you an example, if you just want to look to see what is going on in your sample, let's say here, we were loading the sample and you just wanted to see if we would see Kaiser effect, which means that if the load is going beyond the previous load, if you are seeing, cracking in the sample and how it relates to the other parameters we are measuring. Then you can just have one sensor and that would be fine. I don't know if I put a picture of that. No. Where would you put it if you only had one sensor and one sample? everything. Right? You put it in the middle because you want it to be close to everything that you have, if you only had one. As I said, if you need to localize the events, then you need to have a lot more sensors. Here, for example, this is an example I have shown you before. If you want to see how the acoustic, where actually those energy releases are happening, you need to have a lot of sensors glued on the sample, as you can see. This is a small sample. You see that you have a large number of acoustic emission sensors. So the point is, everything depends on your application, what you want to do and what you want to achieve. Now, going to the fun part. Okay, you went and you bought the right sensor and the right number and somewhat figured out how to place them, use the right coupling. Now the question is, what do we do with the data? One thing that in a lot of applications you need to do is to localize the source, to localize where those cracks are. This is important in hydraulic fracturing, it's important in earthquakes, it's important in acoustic, in non-destructive evaluation a lot of times. Right? So how do we do that? There are certain things we need to do beforehand. So the first thing to do is, after you have your huge data set collected, the first thing to do is to decide which one of those signals is actually an acoustic emission event, which one isn't. Now how do we find out? It's difficult. If you have the waveforms, you kind of can set different parameters and make sure and find out what would work best. I told you an example of looking at frequency domain. They really doing the classification based on frequency domain. I can talk about that for hours, but so this is one thing we have to do first. The second thing, if you want to localize, you have to see where your event exactly starts. Now, when we were doing the through transmission and these sorts of what we were doing, we were comparing always between contact, etc. And you can always plot them, see them, etc. But in acoustic emission, everything is extremely, you have a lot of data. So you have to have something automated. One thing that works very well is this autoregressive IAC. This is autoregressive. AIC, so this is the acoustic emission event, and this is the AIC. And this is a function from statistics, which is very sensitive to any changes in the data. So it's not working as beautifully as you see here all the time. What you have to do, you still have to do some thresholding to first find out where approximately your acoustic emission is. Once you find out, you can apply that and find the onset very accurately. There are other methods people have come up for different applications with different things, but this is something that works very well in a lot of applications that I have seen. And another thing is, if you want to find the source, so imagine you have a source and it can be recorded by several sensors. So one important thing is to somewhat find out whether this is the same event. So if you are looking at your different sensors, what you are recording, is it the same source? Was it the same crack, which appears like this here, there, and so on? You can look at the onset times. That's one way, but it's not very easy to execute. One method that works well is actually looking at something very similar to coherence function I taught you last time. So, why? Look at these three events. We have even number 1, 2, and 3. I guess as human beings, if you look at them, which ones do you think they belong to the same source? And why? Yeah, so that's great, but when you have a million records, then this is hard. And exactly, all of us can see that. But what we see is we are seeing the frequency content. And you kind of see that this is more stretched, they look more similar, because if they were normalized, it would be much easier to see. I think the amplitudes here don't play very well. Another thing that you need to be aware of is that when an event happens, the very beginning, whatever is in the signal, has a lot to do with the event. If you go a little bit later, whatever you see in the later parts of the signal has a lot to do with the medium through which it is actually propagating. So they all would look similar towards the end, pretty much. You are going to see a lot of influences from the medium that they're, so it's not very much related to the source. So what we can do is they actually look at the coherence function, just like the one I showed you. Remember, I used S last time. So it was like S between receiver 1 and 2. You look at the coherence in the frequency domain. Exactly the same formula, and look what happens. So if I calculate the coherence versus the frequency for the first two signals, the numbers in a certain range, they are very large, and if you get the average, it's like 0.7. If you look at the two which are not from the same source, the average is much lower. And this can be automated. You can feed this in, and you can automate it to say which event is associated, which two signals are coming from the same source. There are other millions of other ways too, but this is one of the main ways to see. So stepping back, we were talking about, I was preparing you about source localization. So we need to first identify the event. We need to have a way to automatically know when they start. And also, you will see that if you want to know the mechanism, you have to have a way to know what is the phase. How does it start? Does it go up or down? This is important. Is it P or S? This could be all important. And then you have to know if the two events are coming from, if the two signals are related to the same event. Okay. Now, after doing all of that, you are ready to do localization. If you have only a rod, so in a one-dimensional case, how many sensors would you need to find where this is happening? Don't look at I've written everything down today. That's the problem. I just wanted to save time. But I'm going to ask you a follow-up questions. I mean, don't worry. We need a minimum 2. Try to write the equations for the time. So the time of the event at the receiver number 1 is T1, receiver number 2 is T2. Try to write the equation, see how you would localize in one group. You should be able to do that. Take the velocity as v, the medium velocity just v. That's exactly why I'm asking you to do that. We want to localize. We know where the sensors are, and we want to know them. Exactly. So let me make this clear. Maybe I wasn't clear enough. I got too excited. We have a one-dimensional rod, and you know that there is a crack happening because you put two sensors on both sides. So we know where the sensors are. The distance between the distance is S. Okay. Now the question is, and we use AIC or some fancy method. We know T1 and T2. We have looked at the sensor 1, we found T1. We looked at sensor 2, we found T2. They are localized. Now my question is, how would you go about localizing this in one dimension? There is a point I want to mention in the slide. Don't worry about it. So how many unknowns do we have? I think I can see that everyone did the same. Let me check. I don't know. Okay. How many unknowns do we have? No, because you are 50% right. X1 is an unknown, but X2, we know how. It's just one of X1. Okay. So what's going on? Why do we need then two transducers? Sure. But so we don't need sensor 2? Is that what you are saying? There is something everyone is missing. We know the velocity. I'm sorry. This is important, very important point, but I assume that you know the velocity. If you don't know the velocity, please become complicated. Exactly. Then we would only need one transducer, but I'm saying we need to. Minimum. So minimum, I mean, you can always have more to have redundancy, but we cannot actually do this in one. Why? Don't worry. This is a common thing to forget. We don't know when the event has happened. We don't know T0. We don't know. And that's why I wanted you to remember this, because that's how you remember. We don't know T0. It's not only X1. So X1 over V is not T1. It's T1 minus T0. And that's why we need two transducers in 1D, 3 in 2D, and 4 in 2D minimum. So, yeah, I mean, the equations are simple. I don't even have to write. So if you have T0, it's basically you have T1 minus T0 would be like X1 over V, and then you have T2 minus T0, and X2 is just S minus X1 over V. And the velocity is a big issue, what the velocity is, and it's really beyond what we can discuss here, but there are methods that we can theoretically also can think of.
So with the velocity, for a very simple case, would you just assume the elastic properties and then calculate the
you assume that it's homogeneous. So in commercial, like when you do acoustic emission and you want to get certified, okay, the first thing you do is to measure the velocity of the medium. The second thing is to measure the attenuation, and then you actually go about placing your transmitter. So and you assume that that's the same. That's typical. But there are ways to take that into account. Anyway, very similarly, if you have 2D localization, if this is not very clear, written, this is like T3 minus T1. So you can kind of calculate, if you have 3 transducers, you can calculate the time between each pair. There are hyperbolas, and hopefully they are going to meet at one point. Yes?
Yes, how do you, so I would imagine that they would always make at one point.
They don't.
It seems like a very nice case, but there's the
Exactly.
So how do you deal with like that, the triangular
So this is not really a practical way. You actually cannot do that. You have errors, as you said, they don't really meet here. So what you do is actually you give some margin, and you look at an area to see if the event can be in that area. And then depending on the margin of error, this area can be a small or large. So at the end, you don't end up with one location. You end up with a circle. You say your event is within this range. This is the best you can do. Did I answer the question? Mm-hmm. Yeah, so they actually normally don't meet. I mean, I've never seen them meeting at one point. That would be great, but this is not happening. But what I want to, so these are kind of 1D and 2D. I wanted to go very quickly from the conceptual point of view. But what is the methods that are being actually used, like in practice, is this. And the small note, the small font says that typically we have a lot more sensors than we would need, much more than 4. So what you need to do is to do some sort of optimization. So the way it works is that, first of all, we need a minimum of 4. T0, remember, and then the location, X, Y, Z of the event. So you calculate, using the methods that I will show you, you will calculate at each location what would be the time, right? And then you also have this time measured from the onset of your acoustic emission event, and you have to minimize this distance to see what would be the location of that event. This is the main thing. Now, how would we do that? There are many different methods. There are 2, let's say, important schools of thoughts. One is this grid search. So here, you say, okay, it's a little bit like SAS. You look at digitize your domain, and for each point, for each center, you can calculate what would be the arrival time in all your sensors, right? Everyone agrees with that? You can calculate it. If the event is somewhere, what would be the arrival time in all the sensors that you have? And then you have the measured arrival times too. And there is also the T0 that you have to take into account. Then you do the optimization. This method conceptually is very simple. I really like it because it's very clear, but it's computationally pretty expensive because depending on what kind of resolution you want to have for your events, you have to digitize your domain into very small boxes. And you can imagine that doing an optimization, you have a lot of nodes, it will be energy. So this is one way people do that. That's an example. It's actually done in 3D, but you can see that you get from your events you get this kind of. You can always add the statistics to it. Yes, please.
So this is ultimately to just determine where you want to place your force sensors or what, right, on the spectrum by either. I guess I'm not following.
No. You kind of have to decide on your sensor locations before. Okay. This is a lot of information in a short period of time. I agree. We place the transducers based on the guidelines that we talked about. Coverage, depending on the application, what you want to do with your data. You know exactly where they are. Just like the two on the right. You don't touch them. Actually, one thing about coupling is that you have to make sure that your transducers are not moving, because that would be a nightmare. You can also do. So once you have that, you have recorded a lot of things, right? I showed you how the data looks like. That was from 4966. So you have a lot of things. Now the question is, where are those tracks? Where are those coming from? And one way to do that is to say, okay, this is the specimen. Let's say this is your cube that you are fracturing. You digitize it, and you can actually, what does it say? I hope it doesn't do anything. For each point, you can calculate what would be the time if the event was happening at that location. But you also have measured the times. So then you optimize it. You have to minimize the distance between the time that you have measured and the time you have calculated. And this gives you an estimation of where these events are happening. Any other questions? Please interrupt me. I know I put a lot of words here, so I can go through this quickly, but I'm very much aware of it. So you should ask me. So that's one school of thought, and there are many, many variations. People, depending on their applications, have tried different things, and but this is kind of the main thing. The second way of trying to locate is you say, well, I assume my event is happening here. You calculate the time, and then you try to correct the position iteratively. That is the second method, which is the iterative localization. So how does this work? Don't try to read the things. Let's just look at the formulas. So you assume here it's different. You don't digitize whatever. You assume where the event is happening. It's important that you are not very far off. If your sample is small, you can assume that the event is happening in the middle. So that's okay, right? If it is large, you can look at one of your sensors and see to which sensor it is the closest. Now you kind of can give you an idea where the event can be. Of course, automatically. You can, in acoustic emission, you cannot do anything. We're looking at the data. What does this one say? So everything seems to be good. Okay. So what you do is you assume where the event is. Again, you have to calculate the time. You see the formula. And then you want to see how much to move the location of the assumed hypocenter. Did you say hypocenter or hypocenter? So the idea is to find out how much you would move your assumed location. So you assume the location, you get the TR, and then if you look at the derivative of this time with respect to x, you see the relationship, how it looks like. So you can basically calculate the change in time, how to change the time And from that, how to change the vector of the location of the hypocenter. And if everything is small, this becomes a linearized problem, so it's faster. You can do this faster. And then you have to do inversion, of course. I mean, optimization and inversion is a part of this, and it makes it always complicated. So this is a different school of thought, how it works. This is faster, is not as accurate because of that particular requirement that your assumptions have to be close to where the hypocenter is for this linearized version to be actually valid. But it's the more common used method in practice. And you can see how it works. So G is the matrix of all these partial derivatives, basically. And this is basically written in the matrix form. This is clear? Yes? Okay. So you can do even more with acoustic emission data. If you look at the reference textbook, there is one whole chapter on localization. So if you need more information, this is there. But I hope that the main ideas are there, how this works. This is important. I may give you a small problem in the test, but it will be a step by step. You won't have a homework, so don't worry too much about it. But it's important to realize the concepts of this. The last thing that I want to tell you about acoustic emission is that you can even do more with this data. I wish we had more time to tell you more, but the fact is, from acoustic emission data, we can even say what are the modes of cracking. If the crack is like mode 1, I don't know if everyone is familiar with this. Mode 1, mode 2, mode 3, there's shear, and there are other modes. So how does this work? It's actually quite fun to think about this. Let's just look at the left-hand side. If you have an opening kind of event, then something is like exploding, like here. The sensors which are around this, they should all see like a positive, you should see kind of a similar phase. If they are positive when they are in compression, they all should show a bump like that. Do you agree? Because they are all being pressed. Right? So that's why this phase, this polarity is important if you want to do mechanism characterization. Now if you have a situation where you have a shear crack, so here is shearing like this, depending on where the sensor is, you may have a positive or negative. So places where the sensor is being pressed, you are going still to get the positive, and where it's going to be pulled in a way, you're going to get a negative. So believe it or not, it's possible to analyze the data, and people are doing this for years, nothing new, and get the mechanisms of fracture. I guess this is very similar to in earthquakes, right? How you also characterize the earthquake. So there is, I don't know how it is in seismology, but in acoustic emission, it is similar. Oh, that's interesting. So you can, if you know the location of the sensors, and you know the polarity of the sensors, you have to know the characteristics of them. Then you can do this moment tensor inversion. I'm not going to, this is its own topic. I'm not going to tell you what it is or how we get there, but it kind of it can tell us what kind of fracture, what mode we have. For example, in the two examples that I showed you, if you have a perfectly explosive storm, your moment, your moment tensor would be like diagonal like that. You will have these kinds of, and you can look at these cartoons, you kind of can relate that to this motion. And if you have a pure like shear crack, you may get, depending on in which direction, this would be different. But for this case, you would get these two, so you can see the movement of this before. So the fact is, you are going to get a lot of information from the data. At the end, I have put a table with some of the practical notes. I don't go through this in the class, but it's kind of a good summary of what can go wrong with acoustic emission testing and what to watch for if one day you needed to do this kind of testing. So now to summarize everything we learned, I thought, as always, it's good to kind of reflect on what you've seen in the class. How did you feel yourself? Go back and, especially if this is on YouTube, I hope that it's interesting. Things that I wrote down, some stuff I any questions? Yeah.
I was wondering, so when you're mentioning the moment tensor inversion, what would be the actual numerical values, or what would be the values within that matrix? Would that just be the seismic moment, but if it was a fractal, would it be different?
the point is the different direction. So that makes it, that's how you actually can find the mechanism.
I'm understanding that. I guess I was just wondering what values are actually going into
It's complicated. So you know the I cannot just say, anyway, I can show you. Once you know, no, I think, I'm not sure exactly what seismic moment is, but this is not exactly the seismic moment. I don't think exactly the values are not. What is more important is the relative values. The amplitude itself, at least in these applications, we don't put much emphasis on. I can show you how to do it, but it's complicated. I think maybe 1 or 2 chapters in the book is on this. There is this also, and this is in acoustic emission and OCS started Japanese in the here started doing the four-line evaluation. Okay.